Thank you, Jay Hook. So, welcome to my talk on high fidelity blade resolved wind plant modeling. This work is done at the University of Wyoming with my advisor, Dmitry Mavroplis, and a whole slew of research scientists in our group. I'm the only graduate student working on it. So, why do we care about blade resolved wind turbine modeling? As you can see in this left chart, the cost of wind energy is dramatically decreasing. It's becoming a more viable option for renewable energy. Currently, it produces about 6% of the United States' current total energy, and there's this hope from a study in the DOE in 2015 called the Wind Vision Study. Hopefully, if we do things right, we could have as much as 20% by 2030 and as much as 35% by 2050, but that's kind of a reach. But so some attention that's been brought to this problem of blade-resolved wind farm simulations has come through what Jack talked about this morning on the exascale computing project. And he talked a little bit about the applications. One of the applications is actually this particular problem. And it turns out that our research group has actually had a head start for 3 years in comparison to the actual team, which is being led by NREL and Sandia. And so their target problem is they want to simulate a full wind farm with full rotor models. Yep, what happened there? Sorry, some of my animations aren't showing up. I'll try this. There we go. Okay. So as you can see in this simulation, there's actually a full rotor model, and that means there's a turbine blade that's been geometrically meshed up. And this work was done by our very own Jay Siddharaman at the University of Wyoming in 2013. And what he used was the U.S. Army's Helios software. And Helios is a very controlled piece of software by the Army, so very few people even get to see the source code to even run it. But back then, he was able to do a full wind farm, which was quite a milestone. And this is the Little Grun wind farm. And so how are we approaching this problem? So we do this with a multiple mesh, multi-solver paradigm. In that, we mean for each blade, there's an unstructured mesh, and and for each one of these turbine blades, we mesh it up. And there's going to be a solver particularly to that problem. And in the background, you can kind of see this Cartesian mesh, and that's adaptive, actually. So what we do is we have multiple meshes in the simulation, including the tower, and then there's a background mesh. And what we do is we actually exchange solutions between all of these meshes as it evolves. And so why do we actually care about high fidelity blade resolved? So current low fidelity models cannot capture this phenomena which you see in aerodynamic studies. And so you can see just going slightly to higher inflow velocities, you actually get a flow separation. And these low fidelity models cannot capture this. So it's a really important phenomenon which we want to get to. So for each piece for that, each turbine blade is being solved by an instance through a second order finite volume code called NSU3D, developed by my advisor, Dmitry Mavroplis. It's been a workhorse in aerospace industry applications for the last 20 years. Just to note, we've developed everything, all the codes, completely from scratch in-house, minus one thing, and that's just the AMR structure framework, but the solvers themselves have been developed by us. The other piece, the Cartesian, has been developed by myself and our research scientist, Dr. Mike Brazel. And that handles the adaptive off-body solver, and it's composed of a high-order DG method. And I've developed it to have very high computational efficiency on Cartesian meshes. It has HP adaptation, and what do we mean by that? H adaptation is actually the element size, and so as the solution evolves, you'll see it adapts in time. But it also has P adaptation, so that means in particular cells we can choose a different solution order accuracy to solve those particular flow features. For the off-body standalone code, CartDG, which I developed completely, I scaled it on Mira to over a million MPI ranks. For this problem, it's probably not, I'm getting like 96% strong scalability, but it's not a very fair comparison because I used about 84 billion unknowns. So now that we have the two solutions on the meshes, how do we actually exchange the data? So we did this through an overset assembler code called Tioga, and this is developed by Jay Sitaraman, who I'd mentioned before. And so he worked on taking, okay, now we have multiple meshes, we have different mesh types with different element types, and we have different solution orders, so we actually have to do the interpolation between orders correctly. Sorry, for some reason it's auto forwarding. These plots just show that we can interpolate between the meshes with the exact correct order that is required. That way you can actually capture, you're not losing any information when you're exchanging solutions. So put all together, we call this Wake 3D, the Wyoming Wind and Aerospace Applications Computation Engine. So we can solve various problems from one of our other main projects is helicopters. For the Office of Naval Research, but also we're doing wind energy, and so we've applied this to various problems. Geez, it keeps flipping. Sorry. So the first turbine I want to show you is this NREL 5 megawatt. We did a mesh refinement study. So we chose 4 meshes, this core star mesh, and then we have a family of meshes, so they're all derived from the same mesh. And we're showing power and thrust convergence here. And so this is up to 8 revolutions. These solid lines are the low fidelity model reference power and thrust. And as you can see here, we're actually getting the power, which is red, fairly well. And our thrust is a little under-predicted. But we can work in a manner to try to correct this. And as you can see from the fine mesh, we're using 2.8 million grid points or nodes per blade mesh. So times that by 3 for this blade, and then add a tower, you're getting up to about 8 million nodes per mesh. So on this simulation, we took, this is using in situ, which means instead of dumping all of the volume data, we've actually incorporated Visit's LibSim in situ library. That way we can extract out contours on the fly with the data in memory instead of dumping the whole thing at the end and post-processing. We find this huge for actually running full wind farms. There's just too much data to really handle. So here we actually, I worked with our visualization center at the University of Wyoming. And we placed this turbine simulation actually into a Wyoming setting. And if you're on a desktop computer, it's like a video game. You can actually maneuver throughout the whole simulation and go up and look at the detailed structures of the wind turbine. The next one we studied was the NREL Phase 6. This has been one of the most studied wind turbines. It's not very big. It's about 5 meters long in the radius of the blade. Here it's kind of hard to see, but we have our blue dots showing our power. Here we're matching, the black is the actual experimental data, blue is our results, and this red is that Helios solver. But Helios has been developed for the last 15 years extensively. So we're going to spend a little time to resolve that little wind velocity, which is actually separating in our models. So we're going to spend some time to develop better methods to more accurately capture that. So I talked a little bit about the HP adaptation. So in the wake, this is actually dynamically adapting as we're running the simulation. So here we're actually in the off-body, we're running only second order, and we see that the mesh is adapting. Here I'm showing a second to fifth order solution, and you can see the mesh is kind of adapted, but we haven't let the level raise to the same one as you see from the other one. But here, you see this is second order, and a lot of the details are being smeared out. In the right plot, you see we had less mesh, but we're capturing much more detail in the flow by using a much higher order. Higher order methods actually give you a lot more computational efficiency, and so we want to go that way and to the directions for exascale computing. So the last turbine we studied was the Siemens. This is a turbine that's used in the Little Grun wind farm. Here, under a little bit of guidance of Lee Orff in the back, gave me some motivation to try to work on volume rendering. So this is a volume rendered image. And in this turbine, we compare it again to this low fidelity model, and we get great power and thrust results. And to do this, you really need to actually have a fine mesh. And what do you need in terms of number of counts? Oh geez, keep skipping forward. I don't want to show you that one yet. You need about 2.2 million grid points per blade. So if you take that, times it by 3, you're at 6.6 million. Add 500,000, you're at 7.2 million grid points per unstructured turbine. Okay? So we're going to use that mesh to scale up this system for full wind farms. All right, the scale of this is a 10 by 10 kilometer box, okay? And this is a fly around to show you the scales that we're actually solving to. So going from 10 kilometers, and the finest element on the blade mesh is 7 micrometers. So we're actually doing 10 spatial scales in these simulations, and this kind of shows it. When you zoom all the way into the data, you can really see the details that are coming out for these wind farm simulations. And on the bottom, you can kind of see the adaptive mesh that I took a slice of. So it really shows that this thing really needs large scale, and you can't do that without adaptive mesh refinement. So we tried to stress test this and see how well can we actually scale up to do a full wind farm simulation, okay? So here we say we did a simulation of 6 wind turbines for 9.5 hours, and we say that's perfect scaling. And it can complete about 1.37 revolutions in a 12-hour wall clock time on a total of 2,808 processors. And so we scaled this thing up to 96, 100 turbines, which is actually the goal for the exascale wind project. They want to do 100 turbines, 100 billion degrees of freedom. And our weak scaling compared to 6, going from there, is actually 87%. So we're still really doing a great job of actually solving this problem when we scale up. With weak scaling, you say, okay, I want to do the same amount of cores per turbine. And now if you keep adding turbines with the same number of cores, how well does that scale? So we're doing basically 100 turbines, which is the goal for the project. And a little bit about the details. What I'm showing here is this is time, solver time, to execute a flow solve, we say, of a quarter degree, okay? So for 6 turbines for the near body per blade, this is time, a little bit. These aren't on the same thing, but from here to here, it's the same time. So what happens to the solution of a blade when you go from here to 6 to 96? You see they're pretty much the same, but there's a little blip of something going on here. And it actually turned out that writing just our norms to a log file was slowing us down at that scale. Here is the off body. Again, this mesh is actually adapting in time, so it's growing in degrees of freedom. So we expect a wide base, but the great news is they're staying roughly in the same ballpark when you even add up to 96 turbines. Here's our problem, and we're really pushing our developer to work on this, is this overset. So at 6, it's solving much faster, and this is on the same timeline. And you see it's getting a little pushed out way out there. So it's actually slowing down. But that's kind of expected with an overset code because it's adding more pieces, it's doing 288 meshes, is trying to find the connections between all the grids. And so you got to put in better scalability algorithms in the searches to figure this problem. So our largest one here for the 96 was 45,000 cores on the NCAR Cheyenne machine. The largest one we did run was actually 144 turbines. That's over 577 meshes. and that was 2.6 billion degrees of freedom. That's not the largest overset simulation ever done, but the number of bodies, 577 meshes, is by far the largest that's ever been done. So it's quite a milestone to get to this level. The next thing is with these wind farm calculations, you want to faithfully represent the environment. So we're working on implementing a coupling. The first one is this NREL, the Weather Research and Forecasting Model. We're using the LES version of it because we want to get down to, roughly 10 or 100 down to about 10 kilometers. Second, which is not showing up here, this is oops, I overwrote the thing. This is actually the NREL SOFA code, and NREL SOFA code has been shown to simulate full wind farms, like that low-ground wind farm I showed, but they actually use the low-fidelity blade model, so they're not actually doing the full geometry, and they won't capture those flow separation effects. So our major work is going to put in faithful representation of the atmospheric inflow conditions, and then we're going to do it on complex terrains. So a little bit on the final remarks. I'm thankful for the Blue Waters Fellowship this year. They allocated 50,000 node hours. I've used 50 of them because I've been so busy on other machines. But my plan is to run a long simulation to study the wake effects with 6 turbines very soon. And then once we have that set up, I'm planning to write a proposal to do a moderate full wind farm simulation for long to study wake characteristics and power decreases in these things. So that'll be probably 325,000 node hours. And then if everything is good with that, then we will do a major milestone, largest wind farm simulation ever to date of probably 200 turbines with 1 million node hours. The work that has come out of this is, I literally just finished this paper on Friday, and then I had to put this presentation together. And then we had 2 publications for a conference, more publications to come now that this is really showing that we can scale to this level. I'd like to thank my point of contact, Galen, tremendous help in the NCSA staff with Blue Waters, and of course the fellowship this year has given me free rein to do this research. I'd like to thank our 3D visualization team at the University of Wyoming for giving me that great animation. The in situ was a big help from Intelligent Light, Brad Whitlock and Earl Decay. All this computer time, which I feel like we have quite a bit. We just had the 50,000 node hours from Blue Waters. We had an ASD project on the new Cheyenne machine of 15 million core hours. And then this year we have a whole slew of about 50 million core hours to use on the NCAR Cheyenne machine. And again, this research is supported by the Office of Naval Research for helicopter simulations, and also the Department of Energy for wind farm simulations. So with that, I will conclude and take questions. Thank you.